So is there any noise from my end or the audio is clear?
Audio is clear.
It is clear, sir.
Okay, okay. Yeah, so welcome to the first session of the machine learning techniques course. And so this is a new version of the MLT course. Some of you might have seen the old version. So this will be a new set of videos that we have. So what the plan for today is, I'll just be going over what was covered in the first week, some kind of a summary. That's what we'll do maybe for the first half an hour to 1 hour, depending on how much time it takes. And then we'll go into these questions. And along the way, while I'm going over the content, if you have any questions with respect to specific concepts, you can stop me then and there, and then we can discuss it. Okay, so we can.
Excuse me, sir.
Yeah.
So, in the programming assignment in this MLT course, I can't able to open that file which is given to this, from which the question is asked. So, do we need any specific application or software to open that file?
No, it's a Google Colab file. You must make sure that you are using your online degree ID. So if you just click on it, it should open by default.
So this is opening, but inside this there's a link.
Inside this there is a link. What link?
So this MNIST dataset.
It is also working, right? That's just a Wikipedia link. And this link.
And so in this we are asked some questions like how many sample data sets are there, or this kind of thing. So where can we find these answers from? Because data is not given like this form X-train, Y-train or something like that. The data is, if you will open the link, the data is very different, which is given.
No, the data is X, as I have mentioned, right? So data here is the matrix X. So you have to work with that matrix.
So at the last of this session, if you will just tell me how to do the questions from this programming assignment, then it would be fine for me.
Yeah, programming. See, the plan is currently to do programming on Saturday. So we'll see if we have time. I'll go over it. But ideally, we are planning to do Saturdays for programming since it's optional, right? So not everyone will want to do it. So we will see if we have time. I'll do it.
Okay, sir. Thank you.
Okay, so we get started. As I mentioned, please stop me in between if you want to spend some time on a particular concept. Right, so first 4 weeks of the course is going to be unsupervised learning, and there are 3 parts to unsupervised learning. At least that's what we are doing in our course. One is representation learning, which is week 1, or part of week 1 and week 2 will be representation learning. So PCA, and then we'll do kernel PCA in week 2. In week 3, we'll do clustering, which is basically the k-means or what is called the Lloyd's algorithm. And in week 4, we'll be doing estimation, right? Estimation would involve maximum likelihood estimate, which you learned from stats 2, and some Bayesian estimation, which is again something that you must know from stats 2, but we'll be revisiting these concepts. And they'll be used to explain something called the Gaussian mixture model. And then we'll do what is called EM algorithm, right? So you don't need to know what these are now. I'm just giving you the path that we have for the next 4 weeks. So as far as prerequisites are concerned, strongly advise or rather suggest all of you to revise parts of stats 2 and max 2, especially the max 2 linear algebra part is going to come with you for the rest of the course, right? So things like linear independence, basis, dot products, orthogonality, all these things are stuff you must know, right? Because we won't be spending time on any of these explicitly. Okay, so the first week is about representation learning. So first question is, if you are given a set of n data points, x1 to xn, then our goal is to seek some kind of a representation of these data points, right? So some alternate way of representing them. Okay, so that's what we are calling here as x1 superscript r to xn superscript r. So this superscript r is just denoting a different representation of the data point x1. Okay, so the terminology of reconstruction is also valid here, right? So we will be calling these interchangeably. We'll be calling them representations or reconstructions, right? So the reason we are using the term reconstruction is because that will become clear. I hope most of you have already seen the video. So we are kind of constructing these points again using a different set of principles, right? So that's one justification of calling them reconstructions. So the moment you have a reconstructed set of points or a different way of representing these points, then one way of judging how good this reconstruction is given here, right? So this is a function, right, of the original data points and the reconstruction. So what is this summation that I've written here? What is this term? Yeah, so can someone tell me what this sum is, what each term of the sum means?
Reconstruction error.
Okay, reconstruction error, but what object is it? So what am I computing?
Variance.
Not
Loss.
exactly variance.
Sum squared error actually.
Okay, that's better. Sum of squared errors. So this, what is this quantity?
Loss.
No, square.
Length.
Yeah,
Length
that's
of error vector.
correct. Right. So this is a length square, right? So this is something that we always need to remember, right? So xi is some point and xi superscript r is some other point, right? In d-dimensional space. If d-dimension is hard, you can't visualize d-dimension, so we'll stick to R2. This is some point in the plane. This is some other point in the plane. What we have is the squared length of the distance, or rather the squared length of the line joining these 2 points, right? So this is the sum of these length squares. That is what this, physically, that's what this means. So the idea is what you want these reconstructions to be close to the original points, right? That's the whole idea. The smaller this error value, the closer the reconstruction is to the original data point. Okay, so what is a good representation then? You need to find those representations or reconstructions which minimize this sum. So what value of xi r superscript r will minimize this sum?
Perpendicular values, sir.
Okay, let's not go there. Assume that you don't know PCA, but if I want to
It's
minimize,
exact same. If it is exact same as original.
sorry, if you said
If it is the exact same as the original
exactly.
point.
Right, exactly, right. That's what I was looking for, right? So if you set xi reconstruction is equal to xi, the original point itself, then you can minimize this, right? In fact, that is, you'll get 0 as the reconstruction error. Is this a good representation? This is what we wanted, right? We wanted to minimize the reconstructed error. So is this correct?
Yes, but there is, yeah.
Okay, what is missing? This looks correct, but
So should it be divided by the number of data points?
okay, so that's a minor, yeah, I agree, but this is still scalar multiple of that error, right? So the larger question is, if I set xi reconstructed, if I set the reconstruction to be the original point itself, I get 0 error. So is this a good reconstruction or a representation?
So it does
No,
not represent
because there is no compression.
future points.
Right, good point, right? So there is nothing that we have done here, right? So we haven't represented it at all in a different manner. So what we are looking for, and this is what Arun sir has mentioned right at the beginning of week 1, is that we are looking for some kind of compressed representation, right? So what we mean by that is a good representation should have 2 things. One is, of course, the reconstruction error should be small. The new points should be close to the original points. But that alone is not enough. We also need a large compression ratio, right? So what we mean by that is whatever new representation you have, the space that it occupies should be much less than the space occupied by the original data set, right? So this is, if we remove the second point, then we'll end up with this solution, which is degenerate, right? There is no point in, there's nothing to this. So I'll give you one small example from, say, from the text domain, right? So let's say you have the original Harry Potter and the Goblet of Fire novel, right? So it's some 500, 600 pages long, right? So from the context of generating a representation for this text, assume that this is a big text document. How will you, in the context of what we have been discussing, how will you represent this novel? Do you get my point? So I need to kind of reconstruct the original story, but at the same time, I can't rewrite the whole story from scratch because there's no point in doing that. So what would a reconstruction mean, which is having a large compression ratio?
You pick up
Summary.
the words.
Sorry?
We can write a summary.
Good, right? So that's a good point. We can write a summary, right? So the better our summary, the more closer it is to our original story, the better is our representation, right? So here I have just given one possible reconstruction. For those of you who are familiar with the story, you will know that this is a very, very narrow reconstruction, but still it kind of tries to capture the essence of the original story, right? So this is what we mean by compressing it, but at the same time carrying enough information. So this is also related to the idea of what is called information density, right? So density, we all know from physics, is what? Mass by volume, right? That is what density is. So so in this case, the mass is replaced by information, volume is replaced by number of words, right? So how much information can I pack in a set of words, say 100 words? The more the information I can pack, the greater is my information density, greater is my compression ratio, and closer I will be to the original story, and therefore smaller the reconstruction error. Okay, so that's the kind of a practical way of looking at it. In fact, if you look at machine learning research, something very similar happens. So you will study this in deep learning, which will be a course in the degree level. Words, in fact, entire documents are represented by vectors. So there is a technique called word to vec. So those who are interested can search for this. So there is something called word to vec. So this converts words to vectors, right? The essence of a word is captured in a vector, and there are also, on top of this, you also have what is called doc to vec. So documents to vectors, right? So an entire document, you kind of summarize it and represent it as a vector. And these can be later used to do what is called document classification, right? So given a document, is it a news article? Is it a magazine article? Is it a novel? Things like this, right? So all of this is very important in future work also, right? So representation learning is very essential part of ML and deep learning also. So the basic summary that we need to know is that we need to come up with representations that explain the data, and compression is the way to go about it. And when we try to compress the data, we in a meaningful manner, we also achieve comprehension, right? So that is what the first part of it. So any questions so far?
So why it is important to have a large compression ratio? What is the meaning of that? I mean, there has to be some kind of a limit where we don't lose data, right?
That is true. So we should not lose data, but our idea is to capture the essence of the data and not the exact form it takes, right? So for example, if you See, it also depends on the application. If you want to, let's say, enjoy a novel, right? If you want to read a novel like say Harry Potter and Goblet of Fire, and you want to enjoy the process of reading a novel, then you would not go for a summary, right? So your intent or your purpose is to enjoy the process of reading. But on the other hand, if you want to, let's say, that particular novel is part of an exam, it's part of your syllabus in some English literature course, and you want to give an exam, then maybe what you want to retain is key points in the story, the essence of the story, or a summary, right? So there is loss of data, but more importantly, your intent is different here, right? So your intent is to get the information in a compressed form. So that is what stands out here.
Okay, sir.
Okay, so that's.
So can I ask?
Yeah, please go.
Yeah. So like in representation learning, one of the important elements was after the compression is done, we even retrieve the original data, right, from the compressed format that we have.
We retrieve
like after the summary is done, like there should be a way through which we can retain the original text. Like that element is also an important part.
Okay, good point. So yeah, so this kind of representation, the example that I showed, you cannot do that, right? So you are.
Yeah, we cannot do that.
The information.
We cannot come. We cannot create the original text from the summary of the 5 points that you've mentioned. For
Correct,
example.
correct. Yeah. True. Right. So it's a different kind of representation, but your point is taken. The example is more along the lines of what we mean when we say compression. What are we compressing, and what are we learning out of?
Okay.
Okay. So any other questions?
I have doubt in a presentation. I'm unable to understand the graph in one presentation. Can I ask?
Presentation.
Our videos.
Yeah. We will come to that. So you stop me when I'm discussing something related to your doubt. Have we come across that part?
No, not yet.
Yeah. Okay. So we'll now quickly move on to. Yeah. So the compression idea is now clear. There are different ways of approaching this problem, right? How do we represent this data point? And one way which we have been doing is to consider lines that pass through the origin, okay, and represent these data. So blue color point here is the data point, and red is just the origin, right? So I have a line passing through the origin. How can I represent this data point, blue color point, on the line, right? So that's what, if you recall, sir is meaning by proxies, right? So there is a proxy for this point on this line. So you could have different proxies, right? So this green color is also a proxy. This green color point is also another proxy. So then the question becomes, how do we choose these proxies, right? Which of these should I choose? Among these two proxies for this blue point, which do you think is better?
The one in the first quadrant.
Okay, the one in the first quadrant, right? Why is that better?
Because their length of the curve is less.
Right. So the length is less, right? So this length is nothing but the length square will be the reconstruction error, right? So that is less. So this is a better proxy.
The angle is close to 90 degrees, so you can see.
Yeah. But why is that angle close to 90 degrees? That's because the perpendicular is the shortest, right? So we'll come to that. That's what we are doing next. So when we have multiple proxies, then obviously the question arises, what is the best proxy? And as you just mentioned, the one which is closest, the distance to the line is closest, that is the best proxy, right? And this happens to be the perpendicular, the foot of the perpendicular of the point to the line. Okay, so this is what we call orthogonal projection. So whenever we mean projection in our course, it is the orthogonal projection, right? Or that's what this means. So this image, you should remember, right? Always. So given a point x is the data point, and given a line w, okay, so w is the unit vector in this direction. Okay, so this circle is the unit circle and w is the unit vector. The projection of the point x on the line is this x transpose w, w. Okay, and the error is going to be x minus the projection. Point minus projection is the error. Okay, is this image, does anyone have any questions or confusions with this image? Okay, right, so this is very important and we need to remember this. So once we have this, the error for the best proxy is nothing but the square of this length, right? X minus x transpose w, w, square of this, where always remember this formula holds good only if w is of unit length. If not, this formula is wrong. Okay, so this is something you need to know. So once we have this for a single point, you can extend this to the whole data set.
So this is also used for converting a vector to orthonormal, right? This similar formula.
Your Gram-Schmidt, are you talking about that?
Yes, sir.
Okay, that is, yeah. So the orthogonal projections are used there as a part of the algorithm, but here we are just doing it on one point. On one vector w. Yeah, but this idea is, I think, used in the Gram-Schmidt process.
So if the w is the norm w is not equal to 1, then we have to divide the norm, right?
Yeah, we have to divide by norm w square.
Norm w square. Okay, okay.
Okay, so whenever we use this x transpose w, w as the projection, it always means w norm w is 1. But of course, if nothing is given, then you should not assume that norm w is 1. Okay, so
okay, sir. Okay.
If nothing is given, then we can't assume this. But in general, we'll for these sessions we'll assume that it's 1. Okay. So now for n data points, we just sum this across the reconstruction error for all n data points divided by n, and this is the error for our data set. And what we need is we need to find out that direction w which will minimize this, right? We need to find that direction where this error is minimized. Okay, so far is this clear? Okay.
Yes, sir.
Okay, so now we are just going to do some algebra, which I think professor has already done. I'm just repeating all this. So norm w, so norm of something square is something transpose something, right? So that's what we are doing. So this transpose this, xi minus xi transpose w, w transpose that. So if you simplify, you will end up with an expression like this, right? So xi transpose xi is, in this case, it's a constant because we are minimizing with respect to w and not with respect to the data points. So this is just the way the minimization problem is changing, right? So we started off with this, and then we ended up with this, and we can further simplify this as minimize this with respect to w, the summation minus xi transpose w whole square. Okay, so what will be the next step? How can I rewrite this equation, this formulation?
Maximum of
Negative point.
Right, so you can maximize the negative of that. So we end up with this maximization problem, right? So find that direction where sum of xi transpose w whole square by n is maximized. Okay, so this is where we do some more algebra. We rewrite this as w transpose xi into xi transpose w, and we pull the w out to get this representation. So it's called, what is this thing inside the square bracket called?
Covariance.
Okay, so this is the covariance matrix, right? So
Covariance.
So one important point is this is the covariance matrix provided something happens to the data points. So for what kind of data points or data set xi to x1 to xn is this the covariance matrix? Should the data set be having some specific property x1 to xn?
Center.
Yeah.
And yeah.
So the data is not centered, then this is not the formula for the covariance matrix, right? You have to do xi minus mu into xi minus mu transpose, but assuming that the data is already centered, mu is 0, right? So mu will be 0, so this will be the covariance matrix. Okay, so the solution to this problem is, so the direction W we are looking for, yeah.
Hello?
Yeah.
Sir, in practical scenario, the centralization we have to do at the very beginning, right?
Correct, correct. Yeah, we'll do it prior to the whole thing.
Yeah, okay.
Okay. Yeah, so the solution to this is the eigenvector corresponding to the largest eigenvalue of the.
Excuse me, sir.
Yeah.
Sir, how do you know that it is a covariance matrix? Like, there is no proof given about it.
And no, this is the definition of the covariance matrix, right? So this is xi minus. So if you compute this whole thing, it will be xi minus mu into xi minus mu transpose, right? And that is the covariance matrix by definition. Okay.
How do we know that data is center or not? Given data is center or not?
We'll center it, right? So if it's not centered, we'll center it and then we'll proceed. That is.
I think he is asking about the procedure, like mean equals 0. That thing.
The procedure is you start with some data set that is given to you, you center it, and then you do all the computation that follows. Right?
No, he's asking how to check the given data is centered or not. I think that's his doubt.
Okay, so
if mean is 0, then it's already centered.
Right. So you know how to compute the mean, right?
Means in every question we have to compute. This means in every question we have to compute mean. If mean is 0, then data.
Yeah. So you understood what centering means, right? What a centered data set is. Do you understand what that is?
So one numeric example could help us in understanding better way.
Also, sir, graphically, how it will look like?
Graphically, it will be clustered around the 0 part. So for numerical example, I think you must have done the activity question. If you have done it, then you will know what a centered data set is, right? So I think it is there in one of the activity questions.
Then MLF also, when we compute PCA, the first step is minusing the mean from the data set.
Okay, right. There is no question on centering. I thought there is.
There is a question.
Yeah.
Yeah,
So,
this one.
So how do you compute the mean here? So what is the formula for the mean?
So in all the cases,
Sigma xi by n.
0.
Yeah, you have to add everything divided by number of points, right? That is all you have to do here.
Yeah, that is coming up to 0.
Right, so it becomes 0. If you want to understand it visually, then so the mean in the case of, see, for a 1D case, it will look something like this. If the center of this line is 0, then you will have a bunch of points which are on either side of it, right? You will have some points here, you will have some other points here. So the lengths of these points should be like kind of equidistant from both sides of the origin.
Yeah.
Right. So if it is a 2D case, then what will happen is they'll all be clustered around this. I'm drawing it very symmetrically, but it need not be so symmetric, right? So somehow the sum of all these data points and you divide it by total number, it should be 0. Okay, so that's what we mean by me centering the data set.
Should we also call it normalization, or that's different?
This is one kind of normalization. This is called mean normalization. There are different kinds of normalizations in the literature.
Okay.
So there is something called mean variance normalization, where you subtract the mean and divide it by the variance. So the data set is not just centered, but it has unit variance. So that is also that. But yeah, that's a good point. So this is what we are doing is mean normalization. Okay, so this is.
So
Yeah.
This covariance matrix again. Like I'm asking, how do you know like this is a covariance matrix?
I told right by definition. So covariance matrix. If you go to Wikipedia, you will see the definition of the covariance matrix is, so you see this definition, right? E of xi minus mu y into xi minus mu y. That is the variance. But for if you have d variables, then this is how the covariance matrix looks like. This is by definition, right? In our case, mu is 0. So you will have x1, x2, x1 square, x1, x2, x1, x3, so on till x1, xn. That is what each row will be. If you compute xi transpose, that's how it will look. So this is not we are not proving anything here. This is by definition. This is what the covariance matrix means.
Excuse me, sir.
Yeah.
Sir, I have a doubt. Like
that was in correlation matrix. It was written.
Okay. Maybe there, yeah, but that's the relation to the correlation matrix. So yeah, sorry, this division will not be there in the covariance matrix. So the sigma of x1, sigma of x2, we won't do for the covariance matrix. That's the only difference. There should be a proper formula somewhere here, but see, you have, in fact, you have the actual formula itself. Mx and My, they are centered. Then mx transpose. Of course, the 1 by n is here 1 by n minus 1. We don't need to worry about unbiased and unbiased estimates and all that. But this is by definition, okay? You don't need to worry too much about why it is like this. So you know the formula for variance, right? It's an extension of the variance of a single variable to n variables.
hello, sir.
Yeah.
So, sir, in the first step, like we're trying to find the scaling factor of W for which the error is a minimum, and in the second step, we're trying to find the W itself, like the for which the error is minimum, right?
We are trying to find through the W for which the error is minimum.
Yeah, in the second step, but in the first step, like we tried to find the value of the scaling factor of W. In the very first step, C we're trying to find, right?
Which step you mean? This one?
Before this, I guess the value of C, like X transpose W.
Oh, that's C. That C you are talking about, which value, right?
Scaling factor of W. Yeah.
Oh, that is for in which context are you talking about this?
Like the professor first tried to find the value of that scaling factor C for which we have minimum error.
That is this projection, right? So what you're talking about is projection. So value of C, once you find out the value of C, and you substitute that value, you will get this particular form for the projection, X transpose W by norm W square. And since norm W is 1, X transpose W is the scalar projection of the point.
Yeah. After that, like we're now trying to find the value of W for which the error is minimum.
Right. Yeah. We're trying to find that W for which the reconstruction error is minimum. You're right. Yeah. Okay. So
minimizing and maximizing the error are same thing.
No, minimizing the error will result in maximizing this quantity here.
Okay, maximizing this quantity.
Variance.
Yeah. So yeah, this is the variance, but we'll come to that in a while. Anyway, so far, any other doubts? If not, we'll proceed. So see, once you find a single W, the single W that we have just been talking about is what? The largest, the eigenvector corresponding to the largest eigenvalue, right? So that is what is the main direction that we have been looking at. And for a data set like this, that direction will be something like this, right? So if you solve that optimization problem, you will get this W1 direction. Now, the point is we can't stop with that. We can't stop with this W1. Why do you think we can't stop with it?
Because we might lose some information in the error itself. There might some there might be some information in the error.
Right. Yeah, so that's the exact reason. So what we have been calling so far as errors, right, are not really errors. So this is why the professor actually moves to what is called residues, right? So for example, if you take this case, can someone tell me what kind of data this is?
Sinusoidal.
Yeah, this is some kind of sinusoidal data which has been rotated by some angle, right? So there is information in two directions, one along this first direction, and there is also some information that is there in this perpendicular direction, right? So we can no longer call that error. So one real life example is if you look at petroleum, right? So crude oil extraction process. Once you get crude oil, there are so many derivatives that you can get from it by a process called distillation, right? So you can extract so many other materials from petroleum, and you don't call. So at the moment you extract the most important product, what is remaining is called residue, right? So in a process of distillation, after you extract one item that is of value, the rest is called residue. It's not called waste or error, right? So we are no longer justified in calling these things errors. We have to call them by the right name, which is residue. Okay, so there is some information that is there in the residue also, and we are now going to try and find that information also. Okay, so this is the residue that we have. This is the projection. Xi transpose W is the projection.
Sir.
Yeah.
So can you just slide down to that graph? Yeah. If it is a linear graph, not like this, then we can able to basically extract out all the information in one go, like in one PCA, like principal component one.
Yeah, that is, yeah. If there is only one direction along which all the data lies, then you only need to do it once.
But like here the data is again in 2D, then what's the difference between that linearity and the sinusoidal which we are referring here?
So assume that this is embedded in some three-dimensional space, right? So here for convenience, let's say we have only two directions and there are again only two directions, but assume that this two-dimensional data is embedded in some higher dimensional space, right? In that case, doing this PCA will help us. That's the whole point of PCA, right? So one of the important assumptions that we make is that our data lies in some low dimensional linear subspace, and that's you have to assume that this is what is happening here.
So basically the principle that is the PC1 only, like if I can say, like this is y axis, that is the vertical axis, and the horizontal axis is x. Okay, so the principal component one, basically let's suppose principal component one is try to basically extract out the information of this between x and y. Okay,
X and y. So it is trying to extract some pattern in the data. So I don't get exactly the x and y. What you mean?
This vertical axis I'm talking about, y axis, and the x axis I'm talking.
Okay.
And now there is a kind of a third axis, z axis, because we are talking about the linear space. Okay, so because our data is mapped into the linear subspace.
Okay.
So I'm saying, like, let's say the principal component one is try to find out the information of the first that is between x and y only, and is it like this only, like the principal component is basically finding the information of two axes parallelly?
No, it is trying to find some. So if it is generally in RD, it is trying to find some set of directions along which you can explain most of the data, right? It may be these two, it may be something else. So yeah, but sorry, I didn't get the question still.
Okay, can I try rephrase it? Okay, so I try to rephrase it. So let's say that, like, because it's a sinusoidal data, so we have like data points in three axes. I can say maybe some points are in x and z axis, and some points are x and y axis. Okay.
Okay.
So in the principal component one, we are just basically plotting like the data points which are in xy plane, and in principal component axis, let's say we are basically plotting the points which are in x and z axis. Is it like that, or something else is happening at the back end? That's what I wanted to ask.
Okay. I got it. Can I tell, sir?
Yeah.
Yes. Whatever you are asking, I think PCA is not working like that. Suppose here is the 3-dimension data. Data is spreaded in the 3-dimension. Whenever we compute the PCA, then completely new dimension form. It's not the same x and y. So it's not come to the projection on x and y.
And also, if we see this particular case here in 2D, the principal axis, the W1 that captures the data in the 45-degree angle, that one, like the largest spread of the data, the largest content of the data, and W2 that captures the data in the perpendicular direction, where the less spread of the data.
Yeah. So see, finally it captures maximum information possible in a set of D orthogonal directions, right? So that's finally what you have to keep in mind. If you are in RD, if you are in R3, and you're looking at some 2-dimensional representation, those 2 directions are going to be orthogonal. If that's what you mean by perpendicular, yes, that is what it is.
So what finally it is doing, I'm getting that. But like what we are basically finding in PC1, PC2, and PC3, that I'm not graphically I'm not able to get it, like what we are getting in that principal component.
I'm also having the similar doubt, sir. Like this line which is given in this graph, let's say this is W, and when we do first principal component analysis, then we get a W1 line which is perpendicular to this W, and when the second, then we get a W2 which will be parallel to W1. Then what is the effect of this principal component analysis?
No, here we get only 2 W's, right? Here we are in R2. If you are in R2, you can only get 2 principal components. There are only 2 principal components possible. One is this line W1, another one is perpendicular to this W2. If you are to think about this as some data set that is embedded in R3, then you will again get 2 directions, W1, W2. You will perhaps get one third direction which will be meaningless, right? It won't have any information along that direction.
Okay, sir. Thank you, sir.
So basically what you are losing if you are only finding the W1, that's what I wanted to ask. Because since it's in 3D, so what we are losing?
We are losing several other things, right? There is some information along this perpendicular direction which you are losing.
Okay, that will be captured by W2, right?
That will be, yeah.
Okay.
Sir, in this 2D cases,
yeah.
So W1 will have the projection of all the points along with the W1 line, and W2 also have the projection along the W2 for all the points, correct?
Okay, that's exactly. Yeah. So W2 along the second component, which is perpendicular to this.
Yes.
All these projections. Yeah. Okay, so if you want to understand it a little more, a different way of understanding PCA is that you are essentially rotating your axis. See, before and after PCA, what you are doing is you are still going to end up with a set of perpendicular directions, right? All your D directions are perpendicular. So what is the main difference is that they are all rotated by some angle, and you are rotating it in such a way that in those directions you capture the maximum information. For example, here if you rotate this XY plane by say 45 degrees, you capture the most salient information along these 2 directions. Okay, so there is clearly more information along this 45-degree line and the one which is perpendicular to it than something like this. Of course, it's the same data set, but the way you represent it matters.
So how rotating increases the information? How are we getting more information after rotating?
So here what I mean by information is the variance of the, so there is see here the spread of the data on the x-axis is this much, right? Starting from here to here. Whereas when I rotate it by 45 degrees in this line, along this line, the spread of the data is much more. So this spread is what I am calling as information. So one measure of information that I'm using is how much variance does my data set have along a particular axis.
So if it was horizontal, so the spread was also the same, I think.
Sorry, in which one?
If this data set hasn't been rotated for 45-degree angles, and if it has been horizontal to 0 degree, then also the data should be same, the information or the variance.
The variance along the x-axis will not be the same as variance along this 45-degree line, right? Assume that if I were to stop, see the whole point of PCA is what? You are trying to stop after a certain number of rounds, right? So assume that this is you are in R10 and you are trying to stop after 3 rounds. So you wish to capture maximum variance in those 3 rounds or whatever number of rounds there are. So do you agree that the variance in this direction is more than the variance in the x-axis?
So can you give me any example for that?
This is the example, right? So
Sir, can I try?
yeah.
See, basically, what I understand is like in this case, let us say we want to represent whole data in one dimension. Okay, so what you will be doing anyway? Just a line, right? But if you increase the another axis in terms of PCA or whatever you choose another axis, so you will get more information and you can store more information regarding the data, right? So for example, let's say we have around 100 dimension and you just want to 100 dimension in the sense 100 axes. So in that case, you don't want to deal with 100 dimension data, let's say in your whatever the process you want to do. So in that case, what we can do is we can basically do some kind of let's say in this case PCA to choose the best possible direction in which we can just work with, let's say sir told right 10 to 2 dimension we reduced. So in that case you can choose like 5 to 10 best axes with the help of which you can basically target, let's say you can explain 80% of the data, that kind of thing. Yeah.
Okay, thank you. I understand.
Okay, so yeah, so that's the whole point, right? So the whole point is our assumption is that there are going to be directions, so different directions in which you can look at the data, and we have found out the most important direction, but there could be information in other directions also, and this is what we mean by residues, right? So the residues will now in some sense become the new data points, and then we'll repeat the whole process for the residues. Okay, so this is what is the residue, xi minus projection. Okay, so we call this xi prime, and now we can repeat the process for the whole thing, but before that we have to make this observation. I hope you all see why this is true. The residues are going to be perpendicular to your first direction. Is that clear to everyone?
Yes, sir.
Okay, so the residues are all going to be perpendicular to the first direction. So this is therefore a very important part. So what we can do is for the second round, I'm going to go back to the same maximization procedure. I have to maximize xi transpose w, but this time for my residues, but with the extra condition that I'll be looking for those directions which are perpendicular to my initial direction. Right, if you go back to this image here, I have already found out one direction w1. Now I know that all my residues are perpendicular to this w, so I need to look for those w's which are only perpendicular to w1 and which maximize this expression. Okay, so I hope this is clear. Now what we can do is we can plug in the formula for the residues, which is xi minus projection. Now, what do you think will happen next? Can I simplify this expression further?
Yes. Yes, because the norm is again the dot product.
W and W1.
Okay, W1 transpose W, what will happen to that?
0.
Becomes 0.
Right, so that will become 0 and you'll end up with the same expression that you had before, right? So this is, recall, this is nothing but W transpose CW, right? So the only difference is you are now maximizing it for a W which is perpendicular to W1. Okay, so we end up with the same optimization objective, but your optimizing variable is going to be different. It's for those directions which are orthogonal to W1. Right, so for the second round, your solution will be the second largest, or rather the eigenvector for corresponding to the second largest eigenvalue. Okay, and if you extend this, then your kth direction will be nothing but the eigenvector of the kth largest eigenvalue of C.
Can you visualize the second round of activity? What is it?
Visualization is the best that we can do is it will be perpendicular to this line. Right, in a 3D case, the 3D case, what will happen is that all the residues will be lying in a plane perpendicular to this line. So if you can think about a plane passing through the origin and perpendicular to this line coming out of your laptop, right? So
Sorry to interrupt you. On this contest, I have doubt in video lecture. Could you please explain with that?
Yeah, sure. We'll come to that. But yeah, so
the same what you are explaining the 3D, the same graph is there in the video lecture.
Okay, can you give me the timestamp?
Yeah, fifth lecture, representation learning part 3, 16th minute, part 3.
Okay, part 3.
16th minute. 16 or 17.
Okay.
Representation learning part 3 lecture.
Yeah, that is what I am in. That's what I opened. 1.5, right? Representation learning part 3.
Graph would be there here. 1 second.
Which timestamp?
17, 16 or 17.
Possible algorithm. This one, right?
Yeah, yes, this one. Second graph, yeah.
Second graph, this one.
Yes.
Yeah, how do we...
I have doubt here.
Yeah, what is...
I'm unable to understand how he plotted this graph.
Okay, so... See, you are... Okay, let me take up some set of points and I'll plot this here so that if we have an axis like this, and let's say you have a bunch of points. Say like this. I'll just take 4 points and have some kind of a line that goes through these 4 points. Rather, something like this. So your errors are going to be like this, right? So these are your error vectors.
Yes, this is clear.
This is clear, right? So which diagram then is not clear? So these
Second one.
Yeah. So what the prof is saying is that all these error vectors will be lying in a plane perpendicular to this line.
Yes.
Okay, so I don't know how to, you have to, visualize this. I don't know if there is a,
We can draw now error vectors.
that's what I've drawn, right? So these are error vectors. These are all error vectors. So this is one error vector, something that's longer than this. They'll all lie on a plane. I can't represent that plane because that plane is coming out of the laptop. So
Okay, that's what I'm unable to understand the graph.
okay, you have to, this is something you'll have to visualize, because you can go to, say GeoGebra or Desmos, they'll have this 3D visualization. You'll have to either plot it there, or can you think of something that is coming out of the book or out of the laptop, a plane that is perpendicular to?
No.
Okay, so
Sir, also we can visualize this for 2D only, right? Like we can visualize for 2D, that will be only a line.
That will be only a line. Everything will be collinear.
Yeah.
So whole thing.
And all the error vectors are parallel to the 135-degree direction.
Correct. All of them are, yeah. Right.
If
So
possible, could you please try to show in GeoGebra, if possible?
okay, maybe not.
Because I don't know how to do it in GeoGebra.
Even I'm not very sure, but let me see. There is a plotter facility here.
Okay.
Okay, so see, you have a plane like this, right?
Yes.
Now we need to draw a line, say a vector. Okay, let's see if this vector makes sense. Yeah, so this vector is, okay, arrow size is too big. So can someone come up with the equation of a plane which is orthogonal to this vector? See this, all these 3D softwares, plotting software, right? Only to some extent it can help us. Beyond that, I'm not sure how much of help it can be, but let's see. See, assume for a moment that you have a line. You can see this orange thingy, right?
Yes.
So assume for a moment that that is perpendicular to this plane. That is the direction that we are interested in. Okay, and all your residues are going to be orthogonal to this line, this orange line. Correct?
Yes, theory is okay, but visualization is still not clear.
Okay, no, that is the whole point, right? See, assume that these are the points. Now these points are in 3D, some kind of a how do I put it? Some kind of a DNA kind of a structure. You have visualized, how a DNA strand looks, right? Double helix. Have you?
Yes.
So if you think about so the easiest or the best closest way you can visualize is something like this. So assume that you have some kind of a line that is going through this double helix, through the center of this double helix, right? So see, they have drawn these. You can think about these as the residues in some sense.
Okay.
Okay, so if your data is along this kind of a 3D structure, and your principal component, the first principal component will essentially go right through this center of the data, and if you try to project them, right, you will end up with some kind of a plane on which you are projecting it.
Yes.
Okay, so don't worry too much. I mean, I understand that this you need to understand visualization, but I think I can do only so much with the tools available.
So you can explain with the help of the room reference, like if there is a corner in a room, then basically two walls are basically the x and y axis, and the third axis, which is the wall which is coming perpendicular to those two axes.
Right. Yeah. These things can. Yeah. These are visual aids that you can use to visualize it. Ultimately, I think you have to try it yourself, right? So it's very tough to how much ever I explain, I think it will fall flat. So
It's okay, carry on.
right. So
No need to waste much time. It's okay, fine.
yeah. So this part is where were we? We were here, right? So you need to look at we are now looking at the second largest eigenvalue of the covariance matrix and the corresponding eigenvector, right? So in the kth round, we'll have the kth largest eigenvalue of C, and this is what our representation. This is our representation will look. Okay, so far is this clear? This is the basic idea behind learning representations.
Sir, I have one more doubt, like noted out, but I just wanted to clarify. Why eigenvectors are of that much importance? Like why not any other direction?
Because the eigenvectors happen to be the one which maximizes this objective.
No, that is something I can read also, but like why? Like I'm asking, is there any kind of a proof or maybe kind of a visualization?
See, this comes from what professor calls as the Hilbert min-max theorem. Okay, so that is the mathematical basis for this. But in terms of visualization, you can think about so see the eigenvectors happen to coincide with precisely those directions where the maximum information lies. I am just rephrasing whatever we know. So
and eigenvectors won't change its direction. There is only change in magnitude, but direction, it will stick to the direction. It will never change its direction, right? Eigenvectors.
Not actually eigenvector, but multiplication with matrix and eigenvector, and that eigenvector doesn't get changed.
Yeah, I mean, I'm not sure if that is an explanation for why these are the best directions. I really don't know. So I don't know what is the for everything we can't visualize. See, this is something I want to.
No, actually, just I can tell. When we multiply a vector with a matrix, when it's an eigenvector, it will be a scalar multiple, lambda into the matrix. That means it won't change its direction. Only lambda changes. It will give you a scalar when you multiply with your matrix. That's why eigenvectors are important. I mean, crucial.
That is the definition or something you are explaining what is eigenvector.
Yeah. Question is why is the case that when we try to maximize this, the direction comes out to be eigenvectors? What is the basis for that?
Yeah.
That is what he's asking. I'm not sure about it. So I don't know if there is a deeper intuitive explanation for why eigenvectors turn up, but all that I can say now is that they are important for whatever reasons, right? Okay, so that is the kth round, and you end up with these k directions.
What
right?
is I here? I.
I is the ith data point.
Meaning?
There are n data points, and you are looking at the representation for the ith data point.
The ith vector, you mean?
Vector data point is a vector, right?
Right, sir. Right. Okay.
Right. So yeah. Any other questions? So this regarding this. So if k equal to d, right? Capital K is d, then there is no compression, because okay. So why is this true? Can someone tell me why this is true?
Because the number of variables remain same.
We are iterating for d.
There is no more direction left for the data display.
Correct, right? So we have exhausted all d directions. So there's nothing we are really doing. We are just representing xi in terms of these d basis elements, right? So note that the eigenvectors form a basis for Rd. Should be. I hope you remember this from max 2 days, that you have D dimensional space, you have D orthogonal vectors, then those D vectors will form a basis for that space. So you're just writing Xi in terms of these basis elements, nothing else.
I have a doubt.
Yeah.
For identifying the W1, the first component. So we are first working from the raw data itself and finding the projection, minimizing everything, and found the W1.
Right.
Now, next stage, we are identifying the residue. And from this residue, again, we are projecting and minimizing, again, finding the W2.
Right.
So in that case, why this W1, is it necessary that W1 and W2 will be the perpendicular?
Good point. Yes, it is necessary, because there is a way to establish that. There is some argument that you'll have to go through. But if it turns out that no matter whatever direction you consider, which is not perpendicular to W1, okay, this maximization objective you have, right, that will be smaller than this value if W were to be perpendicular to W1.
Okay, this happened to be like this only. It will be only the case if it is perpendicular.
Exactly. So if it is not perpendicular, then you can,
the risk of error will be much higher.
Higher, yeah,
in
exactly.
the second. Okay.
Yeah. So this can be formally verified. If someone is interested, we can go through that. Maybe not now, but sometime later.
Yeah.
Okay. So.
Excuse me, sir.
Yeah.
So can you revise with what was W, W1 and W2?
W1 and
W2.
Okay, see, W1 is the first direction. For example, in this case, it will be this direction. W, what we are calling W is some direction that is perpendicular to W1, but which maximizes this. So that the optimal value of W will be W2. Currently, what we mean by W is some placeholder for the optimization problem.
So the projection of the points on the line is called W1.
Yeah, the line is called W1. The unit vector along that line is W1.
Okay. And so what about W2?
W2 will be the unit vector along the second principal count.
So the line perpendicular to W1 would be W2.
Yeah, it will be some line that is perpendicular to W1. In R2, in the case of 2 dimensions, there is only one line which can be perpendicular to W1, so it is just this line. But in higher dimension space, you cannot say the line, it will be some line which is orthogonal to W1.
So in higher dimension, there may be one or more lines that would be perpendicular to this W1.
See, there are infinitely many lines perpendicular to W1, but out of these, there will be only one which we call W2.
Okay.
And that W2 is the second eigenvector of the covariance matrix. Okay, so any other questions? We have one final thing, and then we can move on to the assignment. So once you have this representation, right? So this representation is along these k directions, capital K directions. Now, this is how we tie back to the eigenvalues which we have been mentioning so far, which is that what happens to W transpose C WK for the kth principal component. So we know that WK is the eigenvector, right? So C WK will be lambda K WK, and then since WK has unit norm, this will be 1. So the value of the objective function is actually the kth eigenvalue. This is what it means. Now the question that we ask is, all this is fine. Now how do we choose the top k directions? Right? So there should be some way of cutting off the algorithm at some point, right? You can't let it go forever. So the heuristic is choose those capital K eigenvalues which explain 95% of the information in the data set. Okay, this is a heuristic. Please make a note of this. This is needed. And finally, we come to the variance picture for PCA, which is this, right? So can someone tell me what these terms are? There are these n values, right? What are these n values?
Coefficients.
Okay. Yes, I'm looking for slightly better term. Any other guesses? Or
representative and coefficient is one.
representative, okay.
Vectors.
Okay, anything else?
And vectors and variables.
The point where the projection touches the line.
Length of the projection.
Length of the projection. Right. So is it? So does it always have to be positive? So can you call it the length of the projection? Is that right?
Yeah, it can be negative.
Can be negative also, right? So it's some kind of a signed length. So the square of this will be the square of the length of the projection. But you're right. So these are all the scalar projections on what? Scalar projections of the points on
Principal direction.
Yeah. So the kth direction, right? So you look at direction k, the unit vector is wk for that, and you project all these points on that direction. These are the values, right? So what are the mean? If you take this data set and compute the mean, what will be the value?
0.
If it is centered 0.
It is centered 0, right? Yeah. So it is, assume, let's say we have been doing centering it all along, so it's 0. So then what will be the variance?
Square of the term.
Okay, so sum of the squares of this divided by n, right? So that is the variance. So where have we looked at this particular quantity before? Have we seen this before? Or is it a totally new?
Yeah, to maximize
It is the
negative.
Yeah, so this is the thing that we are trying to maximize, right? So this is nothing but wk transpose c wk. So this is what we were trying to maximize. So this is nothing but what is the value of this for the kth eigenvector?
Lambda k eigenvector.
So this is lambda k, right? So the eigenvalues have a very important interpretation, which is that they capture the variance of the data set along the kth principal component. Okay, so this is why eigenvalues are important here. So this is one of the answers to the question of why eigenvectors come up is that the eigenvalues, the corresponding eigenvalues capture the variance in the data set, and we want those directions which maximize the variance. Therefore, the directions that we choose are the eigenvectors, right? So that is one other way of understanding PCA. And we don't just choose any random directions, we choose the top k directions corresponding to the top k eigenvalues. Okay, so there are two equivalent views. One is error minimization, which is the same as variance maximization. And finally, we come to, so in doing all this, where does compression happen? You have n samples and you have d dimensions, you have nd values that you have to store. So where are we compressing this data set finally? So what's the use of PCA?
Decreasing the d values, right?
Okay, so what will be the final number of values I'll have to store for these n data points?
KD plus KN.
D plus KN.
Oh, that is right. So we have KD values for the k principal components, and we need to store the projections for each of these points. There are k into n projections that we'll have to store. So KD plus KN. Okay, so that is what we had for. So is there any doubt in the overall content of week 1?
What is a component, principal component in just a small gist, if you can tell. Like first component, second component, does it mean rounds?
They mean directions, right? So they are the most important directions in which you want to represent your, or rather not you wanting to represent, but the most important directions in which capture the essence of the data, right? So the first principal component is the most important direction which captures most of the information in the data. The second principal component is something that's perpendicular to it, which captures little more of information but less than whatever is captured by the first component. So we need to understand them as directions.
Excuse me, sir.
Yeah.
So like at the end of PCA, now we have got the the principal axis. So now how do we represent those data in this principal axis? I mean, how do we do that?
Oh, okay, so there are either you could do two things, one of two things. So first is there are k values, right? So there are capital. So there are you have capital K directions. So first thing that you could do is you could, for each xi, you could represent it using these k principal components, right? And it would be a direct reconstruction of this ith data point. That is one way of doing it. The other way is just to retain the projections of this data point on the k principal components. Okay, so it may be a little more clear in what I'm saying.
So like you're saying that you have to project those points on those kth axis, right?
Correct. Yeah. So assume that you have n data points and d dimensions, right? So if you will have what is called a data matrix, right? X n by d data matrix. Okay. One way of doing it is convert this into a n cross k data matrix. So this will retain only the projections of these n data points on the k principal components.
Yeah.
Okay, so that is one way of looking at PCA. Okay, any other questions on the concepts?
Yes, one last thing about the PCA.
Yeah.
So let's say that we get some compression of the data after the PCA. So it is not possible to reverse that data in the back original form in the PCA.
Right. It is not a lossless compression, as they say. There is a loss.
So in that case, we can't use this compression in some important file like that compression of the book, like the Harry Potter or something. There was.
So yeah, so that's where we need a little more context, right? So if you remember, I don't know if Professor has mentioned this in the first week or he mentions this in the second week. There are what we call see that. Okay, so there is a larger goal, right? So is this visible? So see, unsupervised learning, particularly what the kind of unsupervised learning that we are looking at is representation learning, right? So the representation learning is going to be fed into some downstream tasks, right? So whatever representation I learn from my data set is going to be fed into some downstream tasks. For example, say classification, right? So I have some images with me. The images are of size, let's say 1000 cross 1000. Okay. Now 1000 cross 1000, I have red, green, blue, 3-channel. So it's a RGB image. So you can immediately see that this is huge, right? Even one image is going to occupy 3 million pixels. Okay,
Yes.
so this is a huge amount of data. When you're looking at, let's say, 1,000 images, even 1,000 images, you are looking at 3 billion float values that you have to store. And if you can just convert it to, say, megabytes or gigabytes, and you'll know that you are looking at a large volume of data. So what you can do is you can run your PCA on this, say reduce it to a much smaller dimension. So you have what is called a representation, right? So this is not just a fancy word that we have coined up for the lecture. You actually learn a representation, which is then your input to, say, some classification algorithm. You're doing, say, dogs versus cats classification, let's say. So this representation, this compressed representation, will be your input to a classification algorithm. Okay, so why am I saying all this? So your original question was convert a novel to, say, some kind of summary is one kind of compression, but how do I know if that is a loss? There is a lot of loss in that, loss of data. How do I know if that is useful or not? Is that your question?
Yes, and actually which domain it is the beneficial to use the PCA. Like one, I understand that it is the image where we can do something, and we can even track the images. So one, I got the image where I can use the PCA, and the book content I can't use the PCA. Is that any other scenario where the PCA is important? And
okay, is there a scenario where
PCA is beneficial to use and something I can do? For example, I can see in the images, even I compress something image, it's possible somehow I can go back in the original, the quality of the image. Even after making fade, I can come back. So it's also, if we use the PCA, I have something, okay, I can come back on the original. What I have seen with the images.
Okay, so yeah, good point. So where, see, I'm not particularly the correct person to answer this, but from a very general machine learning techniques alone perspective, right? Not from an ML practice perspective, but just from a techniques perspective, wherever you have linearity as one of the key properties in the data, or at least if the data set is approximately linear, by linear occupying some linear subspace, then PCA will work. If not, it's a bad idea to PCA.
Okay, so whenever you say that linear distributed, so it's the relation between the 2-3 column, or the between the column wise, or what?
Good point. So they are between the columns. So if you look at, okay, so this is a good question. Okay, assume that your matrix X is of size n cross d, right? Or let's take a concrete example of 100 cross 4, right? So the data lies in R4, correct? There are 100 data points.
Yes, yes.
100 points in R4, right? So this is the data that we have. Now what you're asking is, what do we mean by linearity? So what I mean by linearity is, I'm saying that these 100 points lie in some, okay, let's kind of slightly increase it to R10, lie in some linear subspace of R10. Okay, that is what I mean. Let's say it lies in some, I will be more explicit, in some.
Okay, so you want to say, sir, that so in that 4 is that non-linear, and the rest of 6 column is the somehow linear relation with the first 4 column.
Yeah, so because of the equivalence of row rank and column rank, right? So we are ultimately coming to rank when we talk about independence, right?
Okay.
So what I'm saying here is that these 100 points, let's say, lie in three-dimensional linear subspace of R10, then the rows are, the span of the rows will be in some three-dimensional space, right? Because the dimension of the rows are all what? The rows are nothing but the data points.
Yes.
Right? So the rows will lie in some three-dimensional subspace. Okay, so the range of the dimension of the row space is 3, and because the row rank is the same as the column rank, I can also say that the columns of the matrix, the data matrix, will also have, dimension 3, the span of the columns. But the physical interpretation is the rows, whatever we are talking about here.
Okay, so in that case, you want to see if I can conclude something. For example, suppose the entire data is that situated at the 3-dimension, but in the 3-dimension place, some plane is inclined and all the data is on the inclined plane. So at the end, after running the PCA, I can convert it is in the 2-dimension, because hypothetically that all the point is lying on the some plane, and doesn't matter how the plane is oriented in the 3-dimension, ultimately it is on the 2-dimension.
Right. So, okay, you are talking about R3 to R2 case, like, I mean, R3 to 2-dimension case.
In general, I'm talking R10 to R3, like that. In the 10th dimension, all the point is lying on the 3-dimension linear space, but we are representing on the 10th dimension.
Correct. Yeah. So, yeah.
Yes.
Exactly. Yeah. All of them actually lie in one 3-dimensional subspace, but there is a lot of redundancy in the way you represent the data, and therefore, for some reason, you are able to observe only 10 dimensions. So actually, there is one. See, there is
one question was there. Where is that? There was in question in assignment where the 4 data set was, the 4th feature was the linearly independent, and rest of 3 features is the dependent.
Right.
Asking what is the ultimate after running the PCA, what will be the dimension?
Yeah. So that is this question. Yeah.
Okay. Got it. So in that case, we can say that that data point is ultimately lying on the 4th dimension only. Even it has the seven features, but it is lying on the 4th dimension only, because that rest of 3 features is correlated to the first 4 features.
Correct. Yeah. So only those 4 matter. The rest of the 3, even though you have some values for it, they are not useful.
Okay. Right.
So means there might be chances that
I have a same doubt.
Hello.
So I have a doubt. I have a doubt in practice assignment question number 10, 11, 12, 13.
Okay. We'll discuss that. Yeah. Practice assignment.
Hello, sir. Before that, I have a small
10,
question.
11,
So
12, 13.
Yeah, please, one by one.
Yeah, sir, my question is very small doubt.
Okay.
Yeah, that is the final message what we get, that error minimization is equivalent to variance maximization.
Right.
But these are on which context? Like, can you explain it? Like like variance maximization, it is on the projected data points. So like on which error minimization and on which variance maximization we have to do?
So, see, ultimately we are choosing some d directions which are all perpendicular to each other. Okay, so this is what we are looking for, right? So some d directions which are perpendicular to each other, and on these d directions you are looking at variance maximization. Variance meaning variance of the projections along these d directions, right?
Yeah, so variance maximization is on the projected data points, like after reconstruction. After projecting those data points, on that we will calculate the variance.
Yeah.
And error minimization is on the projected or original data point?
Error is between the projected and original, right? You need both. I mean, you need to look at what is the error in reconstruction. No, So it's the
Okay,
distance.
error in reconstruction.
Yeah. Distance between the reconstructed data point using these k components and the original data point.
Sir,
Okay.
Original here in the sense like the previous point, right? Not the original one. I mean the previous which we have. Let's say we are in the kth axis. So we need the data from the k minus 1.
Yeah, the residues. Yeah. So you do that step by step, and you end up with, at each level you have some residue, and that will be a new data set at that point, right?
Yeah.
Yeah. So that's correct. Yeah.
Sir, I have a small query with the extension of the what Kumar is asking. So, there might be chances where basically compression is not at all possible. Is it like, have you encountered such kind of cases?
That will come in week 2, where compression using main PCA is not possible.
Okay.
Especially where the data is nonlinear, or it doesn't have any. See, the moment this linearity assumption is gone, right? You can't do simple PCA. You'll have to do something called kernel PCA, which is the content of week 2.
Okay.
Right?
Okay.
Yeah.
So basically we have to find some other approach to tackle this particular issue.
Yeah. So representation is a vast area. So what we have done is one kind of representation. So there are, if you go and study neural networks, which comes up in the next course, there are, representation learning is at the heart of neural networks, but it does it in a totally different way. It kind of automates the whole process of learning representations. So there are different approaches to representation learning. PCA is one approach, but very big drawback is that it assumes, strong assumption is the linearity in the data set.
Okay.
See, even if it is not linear, we can still go ahead and do it, but we won't get much out of it. That's the only thing.
Excuse me, sir.
Yeah.
So while we talked about the compression, right? You said that we needed k into n plus t values after doing PCA.
Yeah.
Okay. So you said that we need k times t values for the principal component, right?
K times d is for the principal components. Yeah.
Could you just elaborate on that? Because I didn't quite catch it.
Okay, so there are k principal components, top k. So each one is a vector in RD, right? So you'll have
Okay. This is that. So
yeah. Okay, so coming back to this practice assignment. So practice assignments, what all questions you have problems? Anyone has any questions?
So question 1 and 2.
Question 1 and 2. Did you look at the solution? Was that clear or not clear?
So I'm not getting how answer is coming 40 MB.
Okay, did you go through the, that should be the solution document here.
It's simple.
Okay, so you can go through this. I think this has been explained in considerable detail why this should be 40 MB and right. If it is not clear after this, let me know. We can discuss it.
Okay, sir.
Same with question 2. This has been, so the steps have been given here. So if there is a question beyond that, right? Does anyone have a question with the solution being not clear? Then we can discuss that.
Yeah, one question, sir. In the question first, just extension.
Yeah.
They ask that suppose that we have a 4 bytes of memory of the each pixel, and there is a 100 by 100 matrix is there. So whenever we say that 4 bytes of the each pixel, so doesn't matter, it's contained by the memory, or we change the data. For example, data can be 0 to 255. So if I changing that value in the particular pixel, is that going to increasing memory or not increasing memory? That's
You're going to change the value of the pixel, is it?
Yeah, change the value in the particular pixel, because it is the matrix at the end, and it is the two-dimensional array in the numpy. So and that particular pixel means particular node of the numpy array containing the some value. So and that according to this theory, it is telling the 4 byte of the per pixel means 4 byte per element.
Right.
So if I change that some value inside that element, that overall memory will change or not?
Memory won't change, right? Unless you are changing the type of array itself. Let's say you're changing it from a float array to an integer array, or say float 32. There are some arrays.
No.
No, right?
I'm just working integer to integer only.
Okay, then it won't change. It won't. The memory will remain the same. We're just changing the value, right? So memory won't change.
In that way, yes. So one conclusion after that I got, in that way I can make the some picture and is the high quality with the same memory, means keep the size of the picture same, and even I can increase the quality of the picture, isn't it?
Okay, that's.
I will put on the Discord, sir, this question that what I did it.
Higher, if you take more pixels, right? A higher quality picture, you take more pixels. That increases the memory space of data.
Yeah, I don't know how you will improve the quality. You can only.
Oh yes, let me tell. Yeah, I can tell you how I did it. Actually, in the data set, sir gave the one data set. I took that one of the data set of the two, written the two, and that two picture was that some hazy, somewhere is the very dull picture. So what I did is I wrote the program to change it in the high quality, and it's completely changed. So that's why I was asking.
Okay, but by
Keep
quality,
everything same.
Quality, what do you mean? You mean intensity of the pixel or the?
Yeah, intensity.
Okay.
Intensity, or sometime I change the color also. Blue, green to fade yellow to bright yellow, or the yellowish green to in yellow, like that.
Okay. So that you can do, but I'm not sure if I would call it quality, right? Quality is a very, abstract.
Yes.
Right?
And it's not the intensity. Something is the quality.
Well,
not you can say the
You
quality.
can change the visual appearance of the image by tinkering with the pixels. That you're sure you can do that, but can you make it look? Yeah, right. Yeah, can you make it look sharper or clearer? That I don't think you can do that. Right?
Yeah, clearer, more clearer. I can make.
Okay. All right. Anything else? Any other questions which in practice assignment which are not clear?
I have one doubt in activity questions.
Okay, which question?
Activity question 1.3. Question number 5. 1.3.
1.3 is it? 1.3. Okay.
Question number 5.
Okay. Yeah, what do you think is the answer for this?
I think it has 3.
Okay, what are the 3?
2. Answer is 2.
Yeah, but what is the third one?
I'm unable to understand this because the point is in R3, it will have 3 dimensions.
Correct, but all the points lie on a line, right?
Yes, But the point is having 3 directions, right? Points are in a line, collinear.
It is right.
So sir, why it cannot be 1?
Because there is going to be 2 directions, right? Two opposite directions.
Okay.
Negative.
Positive and negative.
Yeah, I mean, depends on which you call positive, which you call negative, but yeah, the two W1 minus W are there, right? So there are essentially 2 directions. So you have to think about a sphere, right? If you draw a sphere, then that sphere will intersect this line in exactly 2 points.
Sir,
Yeah.
can we understand, sir? I understand this question by the concept of, sir, vector space. So we can say that the W is a vector with in the vector subspace of 3 dimensions, sir. So then it has only 2 independent variables and 1 dependent variable. So the answer is 2.
No, in that case, the point is independently vary on the space, but here point is on the single line. So can we say better way to?
They're all lying on a line, right? So the line passing through origin.
Yes,
and
sir.
that line has two directions, right? When you can, that is all it. So the best way to visualize, in my opinion, is you consider a ball of unit radius centered at the origin, and you pierce it with some needle, right? That needle is going to pierce the ball in exactly 2 points, and that needle is the line that we are talking about. All the points lie on that needle. So what we are asking is how many piercing points will be there, and there will be 2.
1 is enough now. Why 2?
We have 2, right? So that is the question. Can we choose 2? How many can we choose is the question. How many do we need? We need only 1, but how many are available to me? There are 2.
Can you draw the graph and explain, please?
No, see, you have to visualize, right? See, this is a very simple visualization that you can do. Think about a ball, and all the points all the points lie on a line. So the line can be thought of as a needle, and what I'm asking you to do is pierce this ball with this needle. Okay, how many places will the ball pierce the will the needle pierce the ball? One inside and one out, one on the other side of the ball, right? 2. So you can think about it like a globe. So you have a globe, the axis of the axis.
But I cannot correlate with this example with this question.
No,
is it like the front side of the needle and back side of the needle?
See, this is all I'm saying. You have a sphere in 3 dimensions, right? All the points lie on the axis of this globe. How many representatives are there? You have 2. You have one going in this direction, another one going in this direction. See, this is a skill, unfortunately, you have to develop. There are things you can't draw on the paper, right? So you'll have to visualize.
Actually, I took MLF and MLT both in this term, so maybe that's the reason for the confusion.
Okay, but you get this globe example, right? You have an
yes.
Yeah. Okay, any other?
But I'm still not getting the vector is having 3 dimensions. So why not the representative is 3?
No, vector can have 3 dimensions. Dimension is not the same as direction, right? A vector can have only 1 direction. Even if the vector is in 100-dimensional space, it can still have only 1 direction. The direction can be only 1, but the dimension could be anything, right?
For this, you can visualize in your room one line from one corner to the another corner. So that is a line in a 3 dimension.
See, I think you are confusing between dimension and direction. So that is the, I think, main problem here, right?
This representative will have 2 dimensions, right? Here
representative will have
dimensions.
3 dimensions, right? The vector, the representative is ultimately a vector. That vector is lying in a 3-dimensional space. So it will have 3 points, 3 coefficients or 3 components. So that will always be 3. But how many such representatives can you choose? You can choose 2 because, well, you have on a line, you can either go to the right of a line or you can.
But if it is a line, one representative is enough, right?
That's what I said, right? You are not, I'm not asking about how many are enough. I'm asking about how many can you choose, how many are given to you. So you have 10 balls given to you, you want to pick one ball. Of course, you finally want only one ball, but I'm asking you how many balls did I give you? I'm telling you I've given you 10 balls to choose from, right? That is, so the question is how many are available, not how many you want.
Then in that case, 100 are available for this question. I can choose any point, right? From 100. Out of 100, I can choose any point as a representative.
No, they all lie on a line. You can only choose 2 directions, right? There are in a line. Okay, so you can, if you are on a line, you can either look in front of you. Say you are standing in a queue. You can either look at people who are in front of you, or you can turn back and look at people who are at the back of you. There are only 2 ways you can look at it, right?
Actually, length is 1, so there it will be confined in 2 points only. If the length is not 1, then it could be y 100. It could be infinite. In fact.
Then it could be infinite, yeah. But your length, yeah. So
how length is coming here?
Sir, how length change the parameter?
The length of the W. So if
the length of the W, you can divide it.
It has to be units in the unit circle.
Yeah, here it's a unit sphere, right? You see, think about.
Here it is very simple. Like one line is there. You are standing on the middle of the line, so you have 2 directions from in the left side and the right side.
Correct.
Line is one, but from the center of the line, you have 2 directions for about the line.
Correct. Yeah.
It is not that difficult.
It's like the reflection of one fluorescent if you take it in one direction.
Yeah, yeah. Okay, so any other questions in activity or practice that we need to discuss?
Activity 1.6, question number 2.5.
Okay. 2.6, 2.5. I am sorry, right? 1.6.
1.6, question number 2.
Oh, question 2. Okay. Okay.
And point number 5, sir.
Oh, here 5. 1, 2, 3, 4, 5. Okay. So you remember what orthonormal vectors are, right? Those who are
Yes, sir.
Unit norm, right? So norm of W should be 1. So norm of W is nothing but Wi transpose Wi square root of that, right? So
sir.
That is why this is 1.
Okay.
Okay. Any other questions in activity and practice?
So 1.5, question number 3, activity.
0.5, question 3. Okay, which one? Second statement.
Statement second, sir.
Okay, so all the residues are going to be perpendicular to W. Okay, but they need not lie on the same line. So, okay, maybe this is the
No, sir. Statement second, sir. Statement 1 is clear.
Yeah. So for statement 2, let me try to draw this whatever I can. I need a parallelogram kind of thingy. Let me try to do this. Okay, so now do you see can you visualize this as a sheet of paper and a line that is perpendicular to it?
Yes.
Okay, so this is, let's say this is W1. Okay, so this is W1. You have some points, right? Let's draw some points that are in space. So you have to visualize this as in 3D space. I can't bring that 3D-ness to the points.
Yes, sir.
So now the error vectors, right, of these points are, I'm not going to draw the error vectors. They will be perpendicular to W1. That is okay, right? They'll all be perpendicular to W1.
Yes, sir.
But the point is that they need not be on a line. They are going to lie on a plane. So for example, I am drawing the corresponding error vectors as they will look on the plane. So this is the one corresponding to this. This is the one corresponding to this. This is for this, and this is for this. Right? So all the residues, so these are all the residues. Let me draw this in, say, so these dotted points are the residues of these 4 points. Okay, so these residues, if you notice, they're all still perpendicular to W1, but they need not be collinear. They need not lie on a line, which is what this question is asking you. All the residues are collinear. That is, they lie on a line passing through the origin. No, this is false. Only thing we can say is that they are some kind of a plane which is perpendicular to W1.
Okay, sir. Okay.
Okay, any other questions in activity or practice?
Sir, activity 1.1.
1.7. 0.7.
Question number 1.
Okay, what is the doubt?
Hello.
Yeah, what is the doubt here?
Say here, sir.
Hello?
Hello.
Yeah, what is the question here? Like, what is it you don't understand?
Now, sir, now it's clear, sir. Now it's
okay. Anyone else? Anything else? Any other question?
no,
And the collinearity question that we just discussed, right?
Yeah.
In that, if the situation was where it says that the error, like we have done projections, like subsequent projections, like W1, W2, and we reach some WK, in which the error is 0, then like we saw the first WK, kth W, where like the error is 0, then in that particular case, we can say that WK minus 1 will have errors which are collinear, right? Can we say something like that?
So if after k rounds, the errors, if the residues become 0, is that what you're asking?
Yeah. So the k round has a residue of 0.
Yeah. So which means your data lies in some, yeah, in that final round, all of them lie on some line, WK, right? So all of them lie on WK. They are all collinear. Okay. You're asking whether they'll all be collinear then.
Yeah. So if I was just asking. So if the question was like in the kth round, if the residue is 0, that means at k minus 1 round, like it would have been collinear, right?
Yeah, you are right. Yeah. So if the final round, if in whatever, okay, if the residues are 0, then in that previous round, all of them should have been collinear. Correct? Is that what you're saying?
Yeah.
You are right. You are right. You are right. Okay. Any other questions?
Sir, practice assignment question 10. What is the logical explanation of?
Practice assignment. Yeah. So first this. Let us finish this.
Okay.
This point. This. Okay. This programming assignment. Sorry. There is this one question. I don't know if I said the right thing. In question 12, right? I said that we can throw off the last three, something like that I told. So, yeah, so the last three columns are not really needed, right? So first four are enough. Because the last three columns are anyway, just linear combinations of the first four. So they don't carry any extra information. Is that what I told?
Yeah, that's you was discussing sometime earlier that
Okay.
linear collinearity.
Yeah. So okay, so now see the point I wanted to make there was so this did everyone understand this problem, question number 12, and what the solution was, whatever was provided? Hello, is there anyone who had a problem with this question?
Sir, yeah, I have one doubt. Like in the question number 13, it is given that we have in the 13. I think it is 12. Yeah. Yeah. Here, 12. Yeah. So here it is said that four are linearly independent. Four columns are linearly independent, right?
Yeah.
So from there, we can say that the rank of the row is like 4, right?
Yeah, so we can say two things. The first is that the rank of the matrix is 4 because you have 4 linearly independent columns, and you can also say that the rank of the row space is 4, right?
Yeah.
Not the rank, I mean the dimensionality of the row space is 4, and because the row space is 4-dimensional, then we can kind of argue that there are 4 principal components that you will end up with.
Yeah.
Okay, so yeah, so there is still some kind of confusion, but maybe I'll get back. Yeah, so 10th question, right, Kumar, you are talking about?
Yes.
Okay. Yeah, mean of the residues. Yeah. So what is the question here?
So what's the actually want to ask that? Suppose that after estimating the W1 of the first round, what's the mean of the residues? So how to get that it is the what actually it is?
I mean, physically what it means, or
any geometrically or logically also.
Logically we can argue this way, right? So if you have xi, then xi minus xi transpose wi, right? So sorry, w. These are the residues, right? So if you sum this across the endpoints, then this will be 0, right? Because sigma xi is anyway 0. The data is originally mean centered. Now sigma xi transpose w into w is also 0 for the same reason. You can pull w out and argue that sigma xi is 0.
Okay, so this is the same theory that in the beginning itself I can say that summation of 0 because it's the entire data is the 1 second. No, this is the error. Okay, how can you say that? This is the error, and which is the perpendicular to the W1.
These are the errors, right? Errors are the residues, right?
Yes, and this is the perpendicular to the W1. So how will I know that data is actually surrounded like that to the W1, which after summing coming the 0? That means the picture you made that down, no? You want to say that the same picture. Yes. So this is the residue, and the whatever the length is, the length toward the origin, no? Length to the perpendicular to the W1. So how can we say that it is 0, the summation?
Okay, so the what we are summing up according to this picture is this is the residue, right? So this is one residue.
Correct.
And say I'm just drawing two residues here. So this is another residue. Likewise, you have four residues. What we are saying is the sum of these four is also 0, 0.
Yeah, how it is coming the 0 actually?
Mathematically, this is why, right? Because the residue is what? Residue is, this is the formula for residue, right?
Yes.
Take the point. Now, I'm just splitting this as sigma xi. This is one bunch, and minus sigma what? Xi transpose w. Now I know that this is 0, right? Because the data is already mean centered. So I have 0 minus.
Yes.
This is nothing but I can write it this way, right? Xi whole transpose w. See, Xi transpose w times w. You are summing this for I equal to 1 to n. Rather than doing it, you add all the vectors Xi from 1 to n, take the transpose of that, dot product with w, and then you have w. So this thing is also 0, right?
Okay. I will try to think and visualize this thing.
Yeah.
Definitely, I got it. I will try to think visually how it is.
Yeah.
Yes. So one last question. In the question number 5, he was not talking about q prime and the q, the position of the q. So how the relation is possible? The question they ask that in the next question. Yes, question 7. How can we say anything? Because we don't know that q is perpendicular or not. If q is perpendicular, then it is, or either q prime is perpendicular, then it is possible to say.
So q prime is the best representation of p, right? So it is by definition the foot of the perpendicular from p, right?
So q can be the perpendicular also.
No. That is why what we have mentioned is the image is drawn to scale. Right? Because the image is drawn to scale, you have to take this as an acute angle. This is not a perpendicular. Right? Had this image not been drawn to scale, had this q been some arbitrary point, then you are right. Q could also be q prime, and I can argue that way. Yeah, you are. Maybe that should have been made more clear. Is that okay?
Yes. Okay.
Okay.
That was the.
Yeah.
Yes.
Okay. Any other questions? Yeah. Any other questions regarding the practice?
One question in the chat box, Samit asked that question 7 part B. Since his mic is not.
Question 7. Question 7 part
B. I'm not sure that what's his meaning, which it's assignment or the activity. It's simply written on the chat box. Question 7 part.
Okay. Okay, I think we just discussed this, so I believe it should be clear now, or why?
Okay, he's asking that why p prime is 0.
It is not 0, right? It is greater than 0.
Yes.
Is the answer correct? Have we marked it incorrectly? Yeah, so it is greater than 0, right? Q and Q prime are not coincident. They are different. Q is here, Q prime will be somewhere here. And since we have drawn it to scale, meaning you must just take the image as it is. Q and Q prime need not be they are not the same, right? So Q prime, that vector will have a non-zero length. Okay, so for the best fit, you thought Q becomes Q prime. So as I said, right? So Q is some fixed point which is not Q prime. Okay, so if you read the question, Q is not the best representation, right? It is some point. I'm saying Q prime, yeah, maybe that part is a bit confusing, but assume that Q is fixed and I have drawn it according to scale, right? So all right, so any other questions? If not, we'll close the. Okay, I think that is all we had. So we'll meet again on Saturday. Yeah, you want me to explain 13. Question 13 is. Question 13 should be. If you know how dot products work, then I think you should be able to do it, right? So any point on this side of the line, the dot product is going to be positive with W. W transpose X will be positive, and if it's on the other line, W transpose X will be negative. And on the line, since W is perpendicular to the line, W transpose X will be 0. Yeah, so in graded assignment question 5, square of the length, right? So reconstruction error is always length square. Okay, so where is X? Can I assume anywhere? Yeah, here X is. So you have to characterize this region, right? So X, what I'm saying is X, R1 is the set of all X such that W transpose X is greater than 0. R2 is the set of all X such that W transpose X is less than 0. So this is that set builder notation. If you remember from Max 1, there is a set builder notation, right? That is what we have employed here. Then why x1 and x2 given? X1 and x2 are the coordinates. X is a vector. That is why it is written in bold. The bold is vector. So X will have two coordinates, right? X1 and x2. Okay, so I think that's all we have for today. So we'll meet again on Saturday.
Sir, on the Saturday we'll be discussing the programming thing also.
Mostly we'll be only doing programming unless you have any specific questions.
Okay. Yeah.
Okay, so thanks for joining. We'll close.
Thank you, sir.
Hello, what will be the time for this discussion?
It's on the calendar already.
It's 2 to 4 every Thursday, right?
Yeah,
Okay, I think.
it is Saturday 6 to 8.
And Thursday 2 to 4 or 4 to 6.
Yeah, 2 to 4.
Okay. How to update the calendar? Actually, I missed this session actually.
So you can open the portal in laptop or PC.
Laptop.
Yes, and there you can find the links, important links section,
Where I can
and
find?
open the in the course introduction, the course portal.
Okay. Then
Then just open the link saying course calendar,
okay.
general instruction, and important links part.
Okay.
Once you open it in the new tab, it will automatically pop up something saying add this calendar in your calendar.
So every time I will get pop-up for before meeting, huh? To a link will be same for meeting.
No. It will change every time. So once you add this calendar in your calendar application, then you can see all the upcoming events, upcoming lectures.
Okay. Thank you, Mir.
Yeah.